Okay, so we are in the process of finding volumes of solids, but we are finding volumes of particular solids that have lots of symmetry, and that symmetry is aiding us in finding this three-dimensional volume. And last class we were rotating regions and then using a cross-sectional method, which was a disk. We found a cross-sectional area of a disk, and we discovered that if you integrate area, you get volume. So if we can find a cross-sectional area, we can then just integrate to get volume. Now, let's go ahead and take a look here. So we are going to rotate around the x-axis now. The rotations that we were doing on Thursday were around the y-axis, which was important because, around the x-axis. So on Thursday around the x-axis, and that was important because it created a disk very naturally using a vertical element. And so let's continue with that for a second. We'll rotate around the x-axis, and then we'll start rotating sideways and figure out disks that are around the y-axis instead. So let's do this x-axis thing first. So this is kind of just a follow-up of what we did do. So the idea here is that when we rotate around the x-axis, you are creating disks with a vertical element right here. So this vertical integration element, it should turn into a line if I hold it. This is a vertical integration element at a random x. And so when that element rotates around the x-axis, it creates a disk. The radius of that disk is given by the height of the function. So the function right here, this y function, is going to give us the radius of that disk. And the cutout here kind of shows a good representation of that. So you can see the region rotating around, and you can see the disk that's created from that little vertical element or that vertical rectangle. Yeah, question.
So the height of that vertical rectangle is the function 2 minus 2x?
Yes, that's right. So this function right here, this line is a function, and we've written it in the form y equals, so we've written it in a form that's finding y values, so it's finding heights. If we took that function and solved it for x, we'd be finding horizontal distances. So it's like a coin. You can either, one side's the head, one side's the tail. If you solve for y, you're finding height. If you solve for x, you're finding horizontal distance.
So any vertical slice on that will be 2 minus 2x lengthwise?
Yes.
Okay.
So exactly. So the radius will be the radius for any element, no matter where you draw your element, the height of that element or that rectangle will be 2 minus 2x. So it's going to depend on where you put the x. So if you draw it over here, then whatever that x value gets plugged in there, and that will give you the height of that corresponding rectangle or vertical element. So everybody can see sort of the way that these disks are being formed, rotating around the x-axis. And we are going to go to the generic shape of a disk. We know that the area of a disk is pi times the radius squared. So that's our shape. It's disk. Its area is pi r squared. R in this case is given by the function. So the area of this disk is going to be pi times 2 minus 2x quantity squared. So that's the area of our cross-section at x. And if you notice, on the left side, you don't always have to do this, but it kind of helps a little bit. If you look at the left side, the height right here is 2. So when that rotates around, it's going to create a disk of radius 2. And the area of a disk of radius 2 is 4 pi. So if we plug x equals 0 into our area predictor formula here, it should give us 4 pi. Does it? Yes. If we plug in 0 there, we get 4 pi. So that formula is telling us when we plug in x equals 0, we get the area of 4 pi. If we look at the other extreme over here at 1, we should get a disk of no area because it's just a point rotating around the line, so it's not really creating a disk. So we should get 0 if our area predictor formula is accurate. So we come over here, we say, okay, let's plug in that extreme value over here on the right. That's a 1. We get 2 minus 2, which is 0, so that matches. So your area formula should match based on which x's you put in. So now we know the area of the disk at x. And we saw last time that we can now find the volume by integrating that area function on the interval that these disks are created. And when we look at the interval, it goes from 0 to 1 on the x-axis. So we've got a disk for every x value between 0 and 1. And then the integration of that area function will give us volume. So to integrate here, probably the most natural thing to do is to FOIL this out. So we are going to pull out the pi, and then when we square this out, we'll get 4x squared minus 8x plus 4, and we'll integrate that with respect to x. And this will give us, once we do our integration, we use our power rule strategy. So we're doing the add 1 to the exponent thing and divide by the new exponent. And that will go from 0 to 1. Does that make sense to everybody? So add 1 to the exponent, divide by the new exponent. And the lower limit of 0 plugged in is not going to give us anything. Plugging in 0 gives 0. So we will end up with pi multiplied by 4/3 minus 4 plus 4. So our final answer, the volume will be 4 pi divided by 3. That will be the volume of that cone. Any questions or points in that you're curious about, not clear on? So we'll get the cross-sectional area, integrate the cross-sectional area, and we'll get the volume.
So in the question, they will let us know what kind of shape the problem would be so that we can find the area first? Or
They will tell us what the boundary of the region is, and then we have to figure out if our rotation is creating a disk, or it might create a washer, we'll see in a minute, or it might create something called a cylindrical shell also. So we have to determine, usually they're going to tell us use the disk method, use the washer method, or use the shell method. So at this point, we're going to see that we're going to have 3 different cross sections that we'll typically use. Now we have another way to find the volume of a cone. The volume of a cone has a geometric formula to it. Anyone remember what the volume of a cone is?
Pi r squared divided by 3.
Yeah, exactly. 1/3 pi r squared. No, close. 1/3 pi r squared h. Pi r squared would give you the area of a circle, and then if you multiply by h, you get the volume of a cylinder, and then if you divide by 3, you'll get the volume of the corresponding cone. So 1/3 pi r squared h. So that would be our geometric way to get it also. So we could say volume of a cone is 1/3 pi r squared h. So pi r squared h again, that's the volume of a cylinder. And then 1/3 of that happens to be the volume of a cone. So in this particular case, if we wanted to check, the radius of this cone is given by the radius right here. That 2 is the radius, considered the radius of the cone. So we'd have 2 squared. And the height is this distance here, 1. So this would be the sort of standard geometric way to find the volume of a cone. So that just confirms that we did it right. Okay, so let's go to, and I thought, let me just glance back here. I guess I misspoke earlier. I guess we didn't do any rotations on Thursday. I was thinking we did a rotation as our last example. So last Thursday, our cross sections were constructed. We said, here is our base for our solid, and we're going to generate. We're going to choose to put triangles across it, or we're going to choose to put semicircles across it, or we're going to choose to put rectangles or squares across it. So our cross sections were generated. We said put squares, put triangles, put semicircles. And then our first example today is our first with an actual rotation. So when we do a rotation, I mentioned this last time, that if you do a rotation, your cross section is the disk, because we did do one example of that. We had that bullet head thing where the cross sections were disks. So this is the first one where we're really just looking at a rotation around the x-axis. Each cross section will be a disk. So let's try another one. So we are given the region in the xy plane. So they tell us the four boundary curves. Right, so there's 4 boundary curves here. They give us those 4 boundary curves. There's that region. It gets rotated around the x-axis. We're going to think about using the function here as the height of this element or this rectangle at a random x. And as that's rotated around the x-axis, you can see the solid object that it makes. And there I've sort of tried to cut it out and show you what one disk looks like. These images are created. There's a super cool piece of software which is really nice in Calc 3. We'll use it in here for solids of revolution. It's called CalcPlot 3D. It's super great for creating solid objects and graphs of surfaces, CalcPlot 3D. And it's a free piece of software. A guy that I used to go to conferences with got a National Science Foundation grant to create it. So he's been creating the software for the last 20 years, and it's super nice. CalcPlot 3D. And it's free. Okay, so again, we see that our cross-section is going to be a disk. Not a triangle, not a semicircle, a disk. If you rotate a line around an axis that it's touching, you create a disk. If you had a segment and you rotated it and there was a gap, you would create what we're going to call a washer. But if you're rotating around an axis and your segment that you're rotating touches it, it's going to create a disk. So we're taking that blue segment, that blue element, that blue rectangle, rotating it around the x-axis and creating that disk. Area of a disk, pi r squared. Now, there's a lot of pieces to the puzzle that you want to sort of be thinking about. There's a lot of cues that should be going on in your head. One of them is that you are creating a vertical element, so you're creating an element for all the x's between these 2 points. So our integration variable should be x. So in the end, we should be integrating with respect to x. Another thing to think about is that little vertical rectangle has a width of dx. So that's also a cue that you're integrating with respect to x. What that tells us is that our variable, or our letter over here, whatever it is, an R, could be an H in a minute. We'll see some H's. That has to get replaced with whatever the letter is that we're integrating with respect to. So if we're going to integrate with respect to x, we need to replace that R with an expression in x. And that's pretty easy here. The way they've drawn this function, the way they've presented this function is as a y value. So it's measuring height, and height is what we need here because the radius of the corresponding disk is given by the height of that blue rectangle. So that is our radius. So that's going to be e raised to the negative x power, and all that will be squared. So we now have the area of the disk at x. So So that formula there, that's our area predictor formula. If we plug in x equals 0 there, that tells us that the area right here at x equals 0, there is our element. That is 1 unit long, so it's going to create a unit circle. The area of a unit circle is pi. So if we come over here and we plug in 0, we should get pi, and sure enough we do. E to the 0 is 1, 1 times pi is pi. So that's our area predictor formula. And now we can integrate that area formula. And when we integrate area, we get volume. And it tells us that our limits of integration are 0 and natural log of 4. Those are the endpoints of the interval that we're integrating on. Now, we're going to integrate an exponential function, and the natural choice would be to use substitution. The exponent is not just x, it's a function of x. And we've seen last week that we can use something called the reverse chain rule, RCR, reverse chain rule, if the substitution is linear. So I'm going to use RCR, reverse chain rule. Whenever the substitution is linear, you can do this. So RCR only works when you have a linear substitution. Negative 2x is a linear function. Power is 1. So RCR says we can do this. The pi is a constant multiplier, so it comes along for the ride. The integral of an exponential is itself. The derivative of the exponent is negative 2. If you were taking a derivative, you would multiply by the negative 2. We are taking an integral, so we divide by the negative 2. So very similar to the chain rule. We'll call it the reverse chain rule because we're integrating, not differentiating. So that is our antiderivative. Antiderivative of an exponential is itself, and then we have to modify it if the exponent is linear. Now again, RCR only works when you have a linear substitution. So this is a quick little shortcut if you have a linear substitution. If the substitution were more complicated, like an x squared or whatever, any nonlinear function, then you have to go through all the substitution steps. Change the limits of integration, blah, blah, blah. But when it's linear, we've got this beautiful little shortcut, RCR. Those are our limits of integration, 0 to ln 4. And the 0 contributes here. And when we plug in 0, we don't get 0. So the 0 is going to contribute. It's going to matter here. I'm going to pull the coefficient piece here to the front. So negative pi over 2. I'm thinking of that out in front. So I'll put some parentheses here. And in the parentheses will just be the e to the negative 2x evaluated at each endpoint. And we take the difference. So we're going to end up with e to the negative, let's see, e to the negative 2 natural log of 4 minus, so antiderivative at the upper limit of integration, minus antiderivative at the lower limit of integration, so that's e to the 0, which will be 1. And then here we can do a little simplification. Remember your log properties, if you have a coefficient of a log, it can pop up here as an exponent, and then we could cancel the e and the ln. Those are inverse functions of each other, so they would wipe each other out. They will annihilate each other. So what is 4 to the negative 2?
Negative 8.
Say again?
Negative 8.
1/16.
1/16. 4 raised to the negative 2 is 1 over 4 to the 2, which will be 1/16. Right, so so 4 to the negative 2, we're not multiplying them. We're raising 4 to the negative 2 power, so that's 1 over 4 to the 2, so that's 1 over 16. Make sense? Okay, so that's an easy one to make a faux pas on. So we're going to pop that up there, and then the e and the natural log cancel, so we end up with 1/16. minus 1. We will think of the 1 as 16 over 16. So we end up with negative 15 over 16 here. And then we're going to multiply it by what's in front. And the negatives will cancel, and we'll end up with 15 pi over 32. All right, anything there? Anything there that you're curious about? Once again, all the algebra holes are going to come filtering to the top, and all the trig stuff.
Can you explain how you confirmed the area function when you put it in the one?
Yeah, so when we look at the area function from our disk formula, it's going to match, it's a function of x. So if you plug in x equals 0, it's going to give us the area of the disk at x equals 0. And when x is 0, we see the radius of the disk is 1. So when that element of 1 is rotating around, that creates a disk of radius 1. And what is the area of a disk of radius 1? Pi r squared, where r is 1. So that gives us pi. And then we come over here and we plug in that corresponding 0. E to the 0 power is 1. 1 times pi is pi. You see it? And similarly for the other end, the height of the, whatever this height is right here, we would plug that in up here to figure out the height, and we could find the area of that disk. And that's going to correspond to plugging in natural log of 4 right there. Any other questions? All right, well, let's go to another example. So here is, this is going to be called a washer, and it's really just sort of a glorified disk problem. If we think about the area of a washer, the area of a washer is the outer disk's area minus the inner disk's area, right? So it's really just a glorified disk problem. And that's what they're showing us here, that whatever the outer function is, we're going to do pi r squared to get that outer disk's area, and then we'll subtract off whatever the inner function is. Well, the inner function will create an inner disk of pi r squared also. And so you can kind of just sort of see here that if we take a vertical element right there, that vertical element is at a random x, and that vertical element rotating around is going to create this washer. Whatever the outer radius is, we square it. Whatever the inner radius is, we square it, multiply by pi, take the difference, and that'll be the area of the washer. So now, when we do our rotation, we'll have a big disk minus a little disk. So it's still, we're just using disks. So let's go ahead and try one. So we've got this region here. Maybe I should use red for the elements to match what I have in that picture down below. So that is a random vertical element at x, random x. And that red segment rotating around is going to create that red disk. The area of a washer is pi multiplied by the outer radius squared minus the inner radius squared. Big disk minus little disk. When we come over to our picture here, the distance here is going to be the inner radius, and the distance here will be the outer radius. So the closer curve from the axis of rotation generates r sub I. The curve that's further from the axis of rotation creates r sub O. And once again, we have these cues. We're thinking, okay, we've got a vertical element. So that's at a random x. The thickness of that rectangle is dx. So we know we're integrating with respect to x, which tells us we need to replace both of those with expressions in x. Can't be any y's in there. Everything has to be x's. So our area as a function of x, the outer radius is this x to the 1/4, and all of that is squared, minus the inner radius is x, and that has to be squared also. So that'll be r sub o squared minus r sub I squared. Yeah?
Could you explain again the part that tells you that we have to use x?
So the problem tells us that we are rotating around the x-axis. Okay, and so there actually are two choices here. The only technique we have so far if we're doing a rotation involves a disk. So if we know that the vertical element is going to create the disks, the washer being two disks, then we have to draw a vertical element. If the problem was really general and it just said find the volume, you're 100% right. You could say, oh, well, I could draw a horizontal element, but remember that if we're rotating that around the x-axis, if we take a horizontal element and rotate it around an axis, what shape are we getting?
Non-washer.
A non-washer, which is this would be called a cylinder. Right? If we take this segment and we rotate it around an axis that's parallel to it, we are going to get a cylinder and not a disk. And so that sort of tells us why we need the vertical element. Once we get to cylindrical shells, you could actually go either way. But at this point, the only technique we have involves using disks. And so we know that we need a disk, which means this has to be perpendicular to the axis to create a disk, right? And if there's a gap, it creates a washer. If it's touching the axis, it creates just one disk. But if there's a gap, it's going to create the two disks. So let's go ahead and simplify this a little bit here. So power to power, we multiply, so we get x to the 1/2 minus x to the 2. That is our area function. We could confirm it if we want. We don't really, have to, but it's not a bad idea. If you look at these two extremities, we know that the area of the washer here should be 0, because it's not really, there's no segment, there's no distance there. And if we plug in 0, we get 0. And if we plug in whatever this x value is here, which we don't know at the moment, we should get 0 also. Let's find that x value. We don't know that x value yet. Let's go ahead and find it. So the intersection point, right there, if we want to find that intersection point, we set the curves equal to each other. So we'll set x equal to x to the 1/4. We raise both sides to the 4th power. So if we raise both sides to the 4th power, we have that. That's a nonlinear equation, and our typical strategy for nonlinear, push everything left and factor. And this, with the 0 product rule, tells us that x must be 0 or 1. So that tells us that this ordered pair up here is 1, 1. And if we were to take that x value of 1 and plug it in here, we see that we do get 0 for the area of the corresponding washer. Okay, now we know our limits of integration. The interval that we're integrating on, we're integrating across here from 0 to 1. So that's our integration interval. The volume will be the integral from 0 to 1. We can factor this pi out right away. And that is where we're at then. Volume will be the integral of area. Dealing with polynomial-like integration, we add 1 to the exponent and divide by the new exponent. And the interval, 0 to 1. Here, 0 is not going to contribute, so we can focus on the 1. Plug in 1, and we will end up with pi multiplied by the quantity 2/3 minus 1/3. So we will end up with pi divided by 3. That'll be the volume. Any questions? Yeah.
Could you go over again how you got the area formula, the very top one, that r sub 0 squared minus r sub I squared?
Does this formula up here make sense at that stage?
Yeah.
So if you could think of this as pi times the outer radius squared. So that's the area of the bigger disk, the outer disk.
So
And
like
then
the top line of it?
exactly. So
Okay.
so the outer curve is this one up here. So that bigger radius from there to there, that's going to create the big disk.
Okay.
And then r sub I is going to be this distance here. That's going to be the radius of the hole. And so that's what we're going to subtract off, whatever that distance times.
Oh, okay. That makes sense.
It makes sense? So if we look down here at the washer, up here is this right here is the outer radius, and this right here is the inner radius. And so the pi r outer square creates the big area, the disk, the area of the big disk, and then pi r sub I squared creates the area of the inner disk. So we're taking the big disk, subtracting off the whole. Does this substitution make sense here?
Oh, yeah.
Okay. All right. Very visual, this stuff. Okay, let's go to the next one. All right, why don't you all try to set this one up? So write down, I'll come by, and if you've finished your questionnaire thing, I'll come grab them. So write down the outer radius, write down, oh, that's okay, there's no hurry. I'll grab it at break if you're not done. If you're done, I'll grab it. If not, I'll grab it at break. So the setup here is the most important. Obviously, you need to be able to do the math too, but focus on the setup right now. Spend a few minutes trying to get that set up, and we'll see if you've got that figured out. Thank you so much. Oops. Thank you. Thanks. That feels way. Yeah, that looks so great. DX. Yeah, I forgot that was that simple. It's nice when so many things cancel right out.
Yeah.
You never know when that's going to happen. It's not obvious just glancing. But I guess if we thought carefully, we've got two lines that are parallel, so the power in x will be the same. Yep, that's all. Yep, perfect. Yep. Yeah, that one simplifies down very nicely. will use a vertical element at x. And that vertical element at x is going to create an outer radius and an inner radius. The inner radius is always going to be this distance that is going to be generated by the closer curve. So as you're walking from the axis of rotation towards the curve, the first one you hit is the inner radius. And the second one is going to generate the outer radius. So those radii are given by the functions. And so the formula here works out to be super nice. The outer radius is going to be given by x plus 2, and then we square it. The inner radius is given by x, and then we square it. And we have to remember that when we FOIL this, we'll get x squared plus 4x plus 4. So the x squared terms cancel, and we will be left with pi multiplied by 4x plus 4. Pretty simple area function. Integrating a linear function will be pretty quick. And they tell us the limits of integration here are 0 to 4, so there's not a lot of math to be done in figuring out your limits of integration. We will do the power rule. Add 1 to the exponent, divide by the new exponent. And once again, we have a 0 in the lower limit. That's not going to contribute any volume. Plug in the 4, and we'll get 32 plus 16, 48 pi. How's that look? That looks a little too easy for a test question, doesn't it? Felt like everything just worked out too well. But maybe we need some of those on the test. Some problems that just work out so well. All right, any piece there you are curious about? Yeah?
Why don't you factor out the 4 to make it 4 pi?
You can do that, absolutely. You can factor out the 4 and make that 4 pi, and then this will be 8 plus 2, or something. 8 plus 4, whatever it turns out to be. If you factor out the 4 there, you're going to end up with an x and a 1, so you get x squared and 1. Yeah, whatever that will end up being. Yeah, you should get the same answer. Did you?
No.
No! Did anyone else get 48 pi?
I did the same method. I also got 48 pi.
Okay, good. Yeah, there must be a. You figure it out? X squared over 2 plus x. Is that an x?
Plus x.
Yeah, plus x. Yeah. So when you integrate the constant 1, you get an x. That's going to be the. Yeah, that's going to be where your little snag is. The snags. All right, let's rotate around another axis. This is getting boring. Time to turn our head sideways. Sideways reality here. Same general process. If this horizontal element, so our axis of rotation is now the y-axis, and this horizontal element rotates around, so we're using a sleeping rectangle, one on its side, if there's a gap between that element and the axis, it's going to create a horizontal washer. And the formula will be the same. Pi times the outer radius squared minus the inner radius squared. If the element is touching the axis of rotation, it will create a disk, which is that one there. So the washer is big disk minus little disk. And if there is no gap, it just creates a disk. And the area is still the same for disk. Pi times the radius squared. In this case, the radius is given by this function that's measuring sideways. So it's a function of y. It's an x value. So x equals p of y. That's an x value measuring horizontal distance as opposed to measuring vertical distance. So that's the layout. Let's try it. So here is our region. So this region in quadrant 1 given by these 4 curves. There's 4 boundary curves here. And that's going to be rotated around the y-axis, creating this thing, whatever you want to call that shape. And if we take a random horizontal element, so I'll just draw it right there. That's a horizontal element at a random y value, right there. So now we're going to be integrating with respect to y. We're going to imagine all these horizontal elements between y equals 0 and y equals 2. So all these horizontal elements, and those horizontal elements, when they rotate around the y-axis, are creating disks. Right? They're creating these disks that look like that. Oh, there's one. Okay, so we are still dealing with the disk. And we know that the area of a disk is pi times the radius squared. Well, the radius here is this dimension right there. It's that direction. This function is presented as a y value. It's presented as measuring height. The other side of the coin is to isolate x. It's the same function, but now it's presented as measuring horizontal distances instead of vertical distances. If you isolate x, it's measuring horizontal. If you isolate y, it's measuring vertical. It's the same curve, though. So here, you're plugging a y value in to get the horizontal distance, whereas over here, you're plugging in the x value to get the vertical distance. So now it's measuring horizontal, and that's what it's doing. It's measuring the radius. It's measuring the distance from the y-axis over to the curve. That's what that x value represents. So that it is the radius of our disk here. So this will be pi times e to the y quantity squared. So here we go. That is the area of the disk at a height of y. Area of disk, height y.
How do you switch from y equals to x equals?
Solve for x. So it depends on the function. So this particular function, with the natural log, we have to exponentiate both sides. So to get rid of the log, we exponentiate. So we would put in e below each side, and then e to the natural log, those would cancel. And so we would end up with x equals e to the y. So it depends on the function. So if it's an algebraic function like y equals x squared, we would take the square root of both sides and say x equals square root of y. So the general process is solve for x. But then it depends on the particular function on the actual technique. So in this case, because it's a log function, we exponentiate to isolate the x. To get rid of the natural log, we have to exponentiate both sides. Once we have the x isolated, it drops in for the radius. We have an area function. And now we use our generic understanding that the integral of area is volume. So if we integrate this with respect to y from 0 to 2, that will give us the volume of that shape down there. They aren't doing Calc 2. Huh. Is everybody okay with that setup then? This is a natural substitution integral. Let u equal 2y, blah, blah, blah. But we notice that it's linear. That substitution is linear right there. And if that substitution is linear, instead of going through all of the substitution steps, we have our little wormhole, RCR, and just jump through the wormhole here instead of going all through the substitution steps. The integral of an exponential is itself. The derivative of the exponent is 2. Do we divide or multiply by that derivative? Divide because it's reverse chain rule. And then integral limits 0 and 2. I will put the constant pieces out in front here. I'm factoring this to the front. And I'm thinking about plugging in the 0 and the 2 just into that. So factor, or put that pi over 2 out in front. And then we're going to have e to the 4 minus e to the 0. E to the 4 is e to the 4, nothing we can do there. So we'll have pi halves multiplied by e to the 4 minus 1. Questions on that? We're able to find the volume of some, pretty random looking shapes at this point. Okay, so let's go for another one. All right, so horizontal element right there. That horizontal element is at a random y. You guys try to set up the area of that corresponding washer. Let me just mention again that the video from last Thursday, for some reason, didn't save, and just the audio saved. So in D2L, in the announcements, I have a link to last semester's video, and I have a link to just the audio, which you could use with the notes if you want to listen to specifically what we did Thursday. Don't know why that happened. It's never happened before. So everybody's seeing the RI and the RO okay? The RI is the distance from the y-axis to that first curve. And then the R sub O is the distance from the axis over to that second curve, further one. So what is R sub O? What is R sub O? So R sub O is the distance all the way over here. We're measuring horizontal. The way this function is presented, it's measuring vertical. This one's really easy to solve for x, right? So now it's measuring horizontal. So R sub O is just y, and then we square it. So R sub O is y, and then we square it. How about R sub I? Y over 2, exactly. So when we isolate the x here, we divide both sides by 2, we're going to get y halves. So y divided by 2 is going to be the inner radius. It's the distance from the axis of rotation over to the first curve. And then we square it. So that's going to be minus y squared over 4. That part okay with everyone? So whenever we have a horizontal element, we've got to isolate x for the boundary curves. And then And this is going to be pi times common denominator of 4. We'll get 3y squared over 4. So that'll be the area of the washer at y, at a height of y. And then to get volume, we integrate the area function so we can factor out that 3 pi divided by 4. And we're integrating the function y squared on the interval that was given, 0 to 6. The integration technique is the power rule. So we will add 1 to the exponent, divide by the new exponent. Dividing by the 3 will actually cancel with the 3 that's already out in front in the numerator. The 0 is going to contribute no volume. So we will end up with pi divided by 4 multiplied by 6 cubed. And if we just do this old school, we will see that we end up with this. So we get 9 times 6, which is 54 times pi. Yeah.
What happened to the 3 on the 3 pi over 4?
So this is going to be divided by 3, that's going to be multiplied by 3, and those two cancel each other out.
Because 3 over 12 is 1/4.
Other questions? Yep.
Where did the 4 come from in the first place?
This 4 here, that one?
Yeah, how did we?
So this is y divided by 2 for the for this inner radius. So y over 2 quantity squared.
Why is it y over 2? The line is y equals 2x. Y.
So y equals 2x. So we're going to take that y equals 2x and solve it for x.
Oh, okay.
So to solve that for x, we're dividing both sides by 2. So we get y over 2, and then we're going to square that quantity, giving y squared over 4. Makes sense? Good? Ish? All right, here we go. So I do a lot of these graphs in Desmos, and I included that function palette on the left just so you can kind of see how to do things. If you put those curly braces, you can put an interval so that it's not graphing the entire curve, it just graphs it on a specific interval. That's kind of a clever technique that will do that for us. And then if you want shading, you can use inequalities to get shading. So if you're trying to do things a little more fancy in Desmos, you can look at some of those things on the left. All right, so we have our boundary curves, square root of x equals 4, y equals 0. Those are the 3 boundary curves. They create this region, capital R, that's the region. That region is going to be rotated around the y-axis, creating kind of like half a donut looking thing. And we want to find that volume. So there it is. We want to find the volume of that. The red element here rotates around the y-axis, creating that red disk down there. So same story. The inner radius is going to be right here. The outer radius is going to be up there. So the outer radius measures from the axis of rotation to the further boundary curve. The inner radius rotates, is touching the axis of rotation and the inner, the first boundary curve. All right. So this curve up here is y equals square root of x. And if we isolate x, we get x equals
Y squared.
y squared. So now it's measuring horizontal distances. Originally, y equals square root of x is measuring vertical distances, right? It's measuring distance from the x-axis up. When you isolate the x, now it's measuring horizontal distances from the y-axis. So now it's presented as an x value as opposed to here it's presented as a y value. So there we go. Now the right boundary curve is x equals 4. So that's already measuring horizontal distances. Right? X is already isolated. There's no y in that equation. It's measuring horizontal from the y-axis already. So the area of a washer, we always start with the generic shape area. So there's the area of a washer. So now we substitute and we look at the outer radius. So that's the distance from here all the way over to there. Oh, that's 4. No matter where you draw your horizontal element, you're 4 units away from that axis. So we get 4 squared. Inner radius, that's the closer curve. It's horizontal, so we need that function presented as an x value. Boom, right there, y squared. And then we have to square that. So this will give us the area of the washer at a height of y. So if we plug in y equals 0, we are going to end up actually with a disk because there won't be a hole there. If we plug in y equals 2, we should get 0 because that doesn't have any area when you rotate a point around. So if we plug in 2 for y, yeah, we get 0. If we plug in 0 for y, we get 16 pi. Does that make sense? Yes, it does, because this would form a disk of radius 4. The area of a disk of radius 4 is 16 pi. Pi r squared. So it works for the two extremes, so we'll assume it's correct. So now we integrate the area to get volume. The y values go from 0 up to 2. So that'll be volume. Integrate. We get pi multiplied by 16y minus y to the 5th divided by 5 from 0 to 2. 0 contributes no volume. So we will have pi multiplied by, plugging in the 2, we get 32. Here, 32 fifths. That's a terrible thought. 32 fifths. Factor out the 32. If you factor out the 32, we're left with 1 minus a fifth. 1 minus a fifth is 4 fifths. So that gives us a final answer of 128 pi divided by 5. All right, any questions on that one? Yep.
So why do we include the, because we've been working with having like the same, same letter, like x and y's inside of the parentheses, but why in this case we're using the x and the y? So like for x equals 4, you do substitute for the outer, and
So
then for the other one you use y.
So we used x for both of them, right? Both of them have x isolated, right? This has x isolated, and this has x isolated. So this curve right here, we have to write it as an x value. There it is written as an x value. This curve right here, we need to write it as an x value, and it is already written as an x value.
Okay.
see it?
Yes.
Other questions? All right, let's go ahead and take our 10-minute break. And I'll do roll as during the break there as you're coming back in. And let's check this silly thing. Hit pause. All right, so here's another example. The complexity here is that we're not going to rotate around a coordinate axis. So instead of rotating around a coordinate axis like the x-axis or the y-axis, we're going to rotate around a random axis. Maybe I shouldn't say random. It's horizontal or vertical will be our random axes, not like a diagonal line. That's pain. You need Calc 3 to rotate around a diagonal axis. You would need vectors. But here we are going to rotate around this horizontal axis right there. So instead of rotating around x or y axis, we're going to rotate around y equals 1. We are going to have disks. So I'll draw a vertical element here, and this is at a random x. And that vertical element is going to rotate around y equals 1 and create that disk over there. So it's rotating this way. We have cross-sectional disks. The area of a disk we know is pi times r squared. So the setup is all the same. The big difference here is that we just have to remember one basic principle. If you're measuring a vertical distance, it's always upper y minus lower y. If you're measuring a horizontal distance, it's always right x minus left x. All we need are those two basic principles. The general formulas are all going to be the same. So let's see. This is our radius right here. That is a vertical distance. Vertical distance, upper y minus lower y. So the radius is the upper y value, which is 1. The lower y value is that, which will be subtracted off. So it's going to be 1 minus, the lower y value is 1 minus root x, and then all that squared. So everyone okay with that? So this right here is the upper y. And this right here is the lower y. So vertical distance, upper y minus lower y. Where are we? This doesn't sound like college. Huh. Okay, so we'll simplify what's inside the parentheses. So we'll end up with 1 minus 1, which is 0, and then minus a minus is plus. So inside the parentheses, we get that. This will all simplify to pi multiplied by x. So that'll be the area of the disk at x. When we were doing the disks around the x or the y-axis, there was always a 0. So we have to remember here that if we're not around the x or y-axis, this radius is going to be a subtraction of two things. When the axis was the x-axis or the y-axis, then it was a little different. But we do have the same principle, right? Upper minus lower. The volume is then the integral of the area, so the integral of pi times x dx. And we are rotating, we have vertical elements, so our integration interval is right here. We're integrating with respect to x on that interval 0 to 1. So we will end up with pi x squared over 2 from 0 to 1. 0 doesn't contribute any volume, so all we have to do is plug in the 1. So the volume will be pi divided by 2.
How do we know if we're going from around the x-axis or the y-axis?
Well, they have to tell us. So they tell us here that we're going to rotate around the line y equals 1. So that has to be given. Yeah, we need to know that. Must be given. Any other questions on that? Yep.
So on the previous questions, we had two different curves, and we both had each of them individually affected by a exponent of 2. In this case, we have the general equation, and is that just because it's a static line, or is it because we're no longer treating it like a line instead of an axis?
It's because if I'm understanding correctly, it's because we're dealing with a disk instead of a washer. So a disk has
Okay.
r all squared, whereas a washer has little r squared and big R squared and then subtracted.
That makes sense.
So there's two things separately that are being squared as opposed to one thing that's being squared with a disk. So I think that's what you're getting at.
No, and I think
That makes sense? Let's try another one. So here we'll do a random vertical line. So the axis of rotation is given to be x equals 4. So we have our 3 boundary curves. Our 3 boundary curves are generating this gray region. And we're told to take that gray region and rotate it around x equals 4. Now here, different from the last problem, we have a gap. Right? There's a gap between the axis of rotation and the region. When we look at the prior one, there's no gap, right? This region is touching the axis of rotation, so the cross sections are going to be disks. Whereas with this example, the region is not adjacent to the axis of rotation, right? There's this gap here. So that means our cross sections will be washers. There is one cross section that will be a disk, namely this very top one. But in general, we're dealing with washers. We just have one disk there. Okay, so the inner radius is this one right here. It is from the axis of rotation over to the first curve. So that's R sub I. R sub O is the axis of rotation all the way over to the further boundary, which is this vertical line here. All right. So this inner curve is given by y equals square root of x. So this curve right here is y equals square root of x. We are measuring this horizontal distance here, so we need the right x value minus the left x value. The x value on the right here is x equals 4. Right? That's the x value all along this axis of rotation. So on this red segment here, the x value on the right is 4. The x value on the left, we don't have it presented as an x value, so we have to modify it. We're going to multiply, we're going to raise both sides to we're going to square both sides. So that is now the x value on the left. The x value is y squared. All right, so now we have both those ones written as x values. Now let's look at the other curve. Let's see. Again, we already did the right curve. The right curve is x equals 4. How about this left curve? What is that written as an x value?
X equals 0.
X equals 0. So this line right here, that line is x equals 0. That's the equation of that line. So the x value of the left boundary for the green segment is x equals 0. The right is x equals 4. So now we're ready. So the area of a washer, pi multiplied by r outer squared minus r inner squared. The outer radius, that's the green one, is how much? Say again?
0.
This whole green segment is 4. So it's going to be the right x, which is 4, minus the left x, which is 0. So it'll be 4, and then we square it. And another way to think about that is no matter where you draw your representative element, the distance from the left curve to the right curve is always going to be 4. The distance from the left to the axis is always going to be 4. It doesn't matter where you draw your element. Because this is a vertical line, that distance is always 4. The outer radius will always be 4. So the inner radius, all right, the inner radius is here. Again, it's horizontal, and we want distance. Horizontal distance is right x minus left x. The right x is 4. The left x is
Y squared.
y squared. And then that's all squared. So this is green. This is red. So the green is always the whole distance all the way across, which is the distance between two vertical lines. So it's the right x minus the left x, 4 minus 0. The red is also from the vertical right side, which is 4, but the left curve is changing, right? And so that's why we have to use the function value, because it's changing. And then we're going to simplify this. So we'll get pi multiplied by 16 minus. We're going to square this out and distribute the minus all at once. So 4 squared is 16, distribute the minus. The inner and the outer, you have minus 4y squared. You double it, you get minus 8y squared. Then you multiply by that minus sign, so positive 8y squared. The last is y to the 4th, but then you distribute the minus, so we get minus y to the 4th. So that is our area, and those cancel. That'll be the area of the washer at a height of y. Volume is then the integral of that. So we are integrating 8y squared minus y to the 4th dy from y equals 0 to y equals 2. So that is the setup. All right, is there a piece of that that you want more clarity on? Yep.
Can you explain again how we got to subtracting the 4 with the x?
This one?
Yeah, like the entire thing, yeah.
Okay, so this is our outer right there. And then this one is our inner right here. Oh, I wanted that to be red. So that one is our inner. So we're measuring horizontally, so it's always going to be right x minus left x. When we look at the green here, so green is the distance from the axis of rotation to the further boundary curve. So we have the further boundary curve being a vertical line, which means its x value is constant. So the green line, no matter where you draw the green line, it's going to be 4 minus 0, which is 4. The red line is the thing that's going to be changing. Right? If you draw your element right here, then this distance right there is changing. But it's still, this distance right here is what we're trying to find. That is the inner radius, the axis over to the first curve. So the right x value here is 4. The left x value is y squared. So you can draw that element anywhere, but you still have this issue that your inner is going to be whatever that distance is. Right x, it's always 4. The left x, still y squared. It's not a constant. It's changing as you go. So 4 minus y squared in general will then be that horizontal distance. I don't know where that went. Okay. Is that okay with everyone? It takes a few of these. You got to practice these ones. These, if it's obvious to you, that's good. That's generally not the case with these because there's so many. It boils down to a bunch of basic principles. Horizontal is right minus left, vertical is top minus bottom. But applying those basic principles into this more complicated scenario is tricky. And it does just take a bunch of practice. So we'll do our standard power rule integration here. Add 1 to the exponent, divide by the new exponent. The lower limit of 0 gives 0 volume. Plugging in the 2 will give us 8 here. So we're going to have 64 thirds. Minus, that's 32. 2 to the 5th is 32. So minus 32 fifths. Then we just have to simplify that. The easiest way in my mind is to factor out the 32 so that we have 32 pi times 2 thirds minus 1 fifth. And then we get a common denominator of 15. So we multiply that one by 5, that one by 3, so 10 minus 3. No common factors between 32 and 15. That's 3 times 5. There's no 3 or 5 in that. So we're going to get 7 times that. So 224 over 15 multiplied by pi. So that'll be the volume. Woo! We made it. Well, I made it. Hopefully you made it. Can't tell. You guys are poker players.
Yeah, dragged over the finish line.
Dragged over the finish line. Is there a piece of it? If you can't formulate a question, you can just point and grunt. This part, hopefully this part is really routine. If this part's not routine here, definitely do as many practice problems as you can. The integration part should be routine by now. This is the hard part. The setup is always the hard part. And one of the pieces that's funny about this washer thing is that you're measuring these distances that aren't in the region, right? This R sub I is not in the region. Whereas when we're doing the disk method, everything is inside the region. So like when we're looking at this here, right? The radius of this disk is inside the region, which is much less confusing when you're measuring distances that are outside the region. And so for the washer, that's the piece that's a little confusing. You know, when you look at these disks, it's always in the region. So you're looking at, oh, I'm looking at the right side of the region and the left side of the region and the top of the region, the bottom of the region. But with the washers, you know, this R sub I in this case is not in the region. And so that's what makes it feel a little bit, it's easy to get sort of tangled up a little bit. So one of the things to just keep in mind is that principle that, let's see, where were we? I think that's where we were. No, that can't be where we were. Where were we?
That was the vertical.
We were there? Thank you. So one of the things just to keep in mind is that if you draw your inner and outer radius, just look at the endpoints, you know, and don't get hung up with the fact that this red one is not in the region. It's a horizontal distance, so you take the right x minus the left x. The left x is a function because it's changing. Here, the left x is not a function. Right? It's just always constant. It's always 0. So, yeah, it'll take a little bit of practice, for sure. All right, well, let's go ahead and, ooh, the torus. Let's find the volume of a torus, volume of a donut. So we want to find the volume of the torus formed when the circle of radius 2 centered at 3, 0 is rotated around the y-axis. And then it says this little clever comment here, which is going to sound a lot simpler than it is. Use geometry to evaluate the integral. Let's talk about that for a moment. Let's come down here for a minute and look at an example. So let's suppose we have the following setup. Let's suppose that we have a semicircle from -2 to 2. This curve is y equals the square root of 4 minus x squared. That is the equation of the top half of the circle of radius 2 centered at the origin. Radius 2 centered at the origin, the full circle is x squared plus y squared equals 4. But if you isolate the y and you choose the positive square root, you get the upper semicircle. Everyone okay with that? If you were looking at the lower semicircle, which we're not going to, but let's just suppose we were, what would the equation of the lower semicircle be? Just negative, but the same thing, correct? Same piece as the top, just multiplied by -1. Okay, so if we wanted the area of this semicircle using calculus, the area of that semicircle using calculus, we just integrate the function and we get the area beneath the curve between it and the x-axis. Right? This area, let's find this area here. So that area, it's just the integral of the curve, right? -2 to 2, this function. Do you agree with that? And that's what you did in Calc 1. If you integrate a curve, you get the area between it and the x-axis. This is not integrable at this stage. You don't know how to integrate the square root of a square. This is something we will learn in this class called trigonometric substitution. We'll have to use a really clever technique to do it. But this we don't know how to do at this stage. We can't integrate the square root of a square. Which again is the hard part about integration. It doesn't look that complicated, but we can't integrate that right now. You need a special technique. But you do know how to geometrically find the area of a semicircle. What is the area of a semicircle?
Pi r squared.
So we're going to do pi r squared divided by 2, right, for a semicircle? Yeah, so that radius is 2. So we're going to get pi times 4 divided by 2. So we're going to get that area is 2 pi. So what they're telling us up here is you will get to an integral that you can't do directly, but you can look at the geometric interpretation and use standard geometry. So that's what they're telling us, is that sometimes you can't integrate the function that's given, but you can draw a picture and geometrically figure out what it represents.
So wait, why aren't you able to integrate that? I'm a little confused.
What would be the antiderivative of that?
Well, could you not break it up into 2 separate terms?
Oh, the pain. Can you take the square root of a sum and split it?
No, you cannot.
Right? You can't separate a square root of a sum or a difference. You can't distribute the square root symbol. If it was a product, the square root of a product, you can take the square root of each piece. But if it's a sum or difference, you can't break that square root apart.
Can you now use a substitution?
So what would be the derivative of your substitution?
Negative 2x.
Negative 2x. Is there an x on the outside of that square root to absorb that substitution?
No.
Right, substitution works when you take the derivative and that derivative is somewhere in the integrand. And so if you did that would be the natural substitution. Your derivative would be negative 2x, but there's no x out in front. So if there was an x in front of this, then substitution would work perfectly. But because there's no x in front of that square root, substitution's not going to work. But, so this is what they mean by this. We need to be able to understand the geometric interpretation from Calc 1 of what an integral represents. Sometimes it's going to represent the area of a shape that we know how to find the area of. And so we can use that to our advantage. All right. So, now, there's also another hidden thing here that you will look at in some point, depending on what your sequence is. But there's a very cool theorem called the theorem of Pappus. And it says if you create a solid object by rotation, you can find the volume of that solid object by taking the area of the generating region. So we've got this disk and it's rotating around. You could take the area of that generating region and multiply it by the average distance traveled by the points in that region. In other words, take the center of mass of the region, figure out how far the center of mass travels, and then multiply that by the area of the disk. So the area of the disk multiplied by the path, the average path. The average path is given by the center's distance traveled. So the center would travel 2 pi r, and then multiply it by that area. That would also get you to the volume. Okay. So that's sort of a geometric shortcut in this very specific case. But that's not what we're doing. So we have this region. There's our generating region. Rotate that around the y-axis, we get a washer. Now, we are going to use a horizontal integration element because that integration element horizontal rotating around the axis is going to create the washers. We can't use a vertical element yet because if we rotated a vertical element around a parallel axis, we would get a cylinder and not a washer. Right? 2 verticals, we're going to get a cylinder. We need a vertical and a horizontal so that we get a washer. So there is our integration element right there. That is going to rotate around the y-axis and create a washer. So that washer is going to have an inner radius right here and an outer radius right here. So there's the outer radius all the way across. And there's the inner radius right there, not in the region. Now we can use some symmetry here. We can say that the upper half of this generating region is going to create the top half of the torus, and it's symmetric to the lower half of the torus. So we can integrate. We will be integrating with respect to y, so we could integrate from 0 to 2 and then double it. So if we integrate 0 to 2, we'll get the top half, and then we can double it to get the full torus. All right, so let's set this up then. So the area of a washer, we know that that's pi outer radius squared minus inner radius squared. Outer radius, that's the green. Outer radius is green. We're measuring horizontally. That means right x minus left x. The right x is this curve right here. The right x is that purple curve. The right side of a circle, you take the equation of the circle, so the center is 3, 0, so we have a shift of 3 to the right. If we want the right edge's equation, we solve for x. And when we solve for x, we're going to get x equals plus or minus, we're going to get the plus or minus the square root thing, plus 3, when that 3 is added to the right side. So the right side of the circle is given by that x value. The left side of the circle, the one in orange here, is that equation. So the outer radius is this green distance. Right x minus left x. The left x is 0. So we are going to have pi multiplied by that thing squared minus the inner radius squared. The inner radius is that red distance right there. That's from the y-axis to the left edge of the curve. Well, the left edge of the curve is this one right there. So it's going to be that minus 0, but then we have to square it also. So we're going to have 3 minus square root 4 minus y squared, quantity squared, all of that. So that is going to be the area of the washer. Everyone okay with that? Look at that for a second. Now this is, the left is 0, which is nice, right? That's the y-axis. So it's going to be the orange curve minus 0. It's going to be the purple curve minus 0. So that's a little bit simpler. We're not between two non-zero boundaries. Now we have to do the math here, do the algebra. So we end up with pi times. That one is going to be 9 plus 6 times the square root. And that square root on the inside, we have 4 minus y squared. Plus, when we square the square root, we get what's inside the square root. So that's the first one squared. The second one squared, let's not distribute the minus sign yet. There's too much happening. So let's square this and leave it to the right of that minus sign. So we square that, we get 9 minus a times b times 2. Algebra technique. Often they call it foiling. And then when we square that last, we get plus 4 minus y squared. So we have that mess. But there's a lot of simplification in that mess. This is a 9. This minus distributes to make that a negative 9, so those will cancel. This 4, when this minus is distributed to that 4, those cancel. And similarly here, that minus y cubed is going to cancel. When this minus distributes, that becomes a plus y cubed, y squared, and those will cancel. So the only things that don't cancel can add together. So we have 6 times the root plus 6 times the root, which gives us 12 times the root. So that is the area function. That's the area of the washer at a height of y. So we just have to integrate that. But that's a function we can't integrate. Square root of a square, we can't integrate it. Sebastian?
Where did the 6 came from?
Foiling. When you do a plus b squared, you get a squared plus 2ab plus b squared. Is that you remember? So if we FOIL like that, we get that double a times b. So in this case right here, we're thinking of that as a and that as b. So we get a squared, and at the end we get b squared, and in the middle we get a times b times 2. So that'll be the FOIL technique that generates that doubling of that middle term. And then the volume, we're going to double it. So this is by symmetry. So this is the upper and lower. So we're going to integrate from 0 to 2 this function. which we can, of course, at least, we'll clean it up in a second. I want to just make sure you see the doubling out in front. So we get that. This will give us 24 pi multiplied by the integral 0 to 2 So here is where we are using the geometry. So that thing represents the area of what? Let's draw a picture. So this function in here is x equals the square root of 4 minus y squared. So if we were to square both sides, blah, 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 that's going to give us the circle of radius 2 centered at the origin. So we have a circle of radius 2 centered at the origin. And x equals this thing is that the right half, the left half, the top half, the bottom half? What piece of this circle is that?
Top
Can't be the top half because top right half. If we isolate x, this is a function of y. And if you say the top half, that's not a function, right? The top half, when you talk about a function of y, it has to pass the horizontal line test. So x equals the positive square root is going to give us this. It's going to give us that. So that curve is the right half of the circle, radius 2 centered origin. Now these limits of integration go from 0 to 2. That's up there at 2, right? So the 0 to 2 is right in here, 0 to 2. So they say integrate the right half of the curve, but only from 0 to 2. So this is what we will get. That integral represents 1/4 the area of a circle of radius 2. And what is the area here? It's going to be pi times r squared. That's the area of the full circle. Divided by 4. That will give us the area of that quarter circle. So this is 24 pi multiplied by pi. So this is the volume of the torus. That one might take a little looking at multiple times. But, so let me ask one other, so we talked about this theorem of Pappus for a second. Tell us what somebody tell me what the area of this disk is right here.
4 pi.
4 pi. Now imagine this center of mass. The center of mass for a disk is right in the center. That point is 3, 0. How far does that point travel if it rotates around this axis? 6 pi. Because it's 2 pi r for a circumference. So 2 pi r, that is 3 units from the axis of rotation, so 6 pi. So the center of mass travels 6 pi. The area of the disk is 4 pi. 4 pi times 6 pi, 24 pi squared. So that's the theorem of Pappus thought process. All right, so look at that carefully. Make sure you understand we are going to see a lot of stuff with that, with foiling. Foiling's simple when things aren't, messy with square roots, but it's still the same process. So make sure you can jive with that process.
Why is that simplified by again?
This right here.
Yeah.
So circle of radius 2 centered at the origin is this. The right side of the circle is x equals the positive square root. So if you were to integrate this from -2 to +2, you would get the full semicircular area. but this integration is just from 0 to 2, y values, 0 to 2. So the curve that we're integrating is the right half, but we're only doing the top half of the right half. And the area of the circle of radius 2 is 4 pi. We only want a quarter of that. So we get pi. Yeah. Let's get out of here. That's scary. All right.
So does that equal the full area of the torus?
Full volume of the torus.
Full volume.
So, because we did that 2 out in front that doubled it. So first we found that, so that 2 out in front was the symmetry multiplier. So we get the full volume of the torus, 24 pi squared. Yep. All right, now that we have washers dialed, let's go to shells. So cylindrical shells. Cylindrical shells, although they are not cross sections in the way we've been thinking of slicing and getting a disc or slicing and getting a washer, instead these cross sections are going to be nested cylinders. So it's kind of like coring something, where you can imagine all these cylinders nested to create your solid object. So instead of a bunch of stacked discs or stacked washers, instead we're going to be thinking of these cylinders that are nested to create our solid object. So if we want the volume of that bell, and we choose a vertical integration element, so we do this vertical element right there, that rotates around our axis and creates a cylinder. And so it's the same process. The geometric shape now, instead of being a disc or a washer, is a cylinder. And we do the same type of thing. We find the area of our geometric object. So the area of a cylinder is the circumference of the base, 2 pi r, times its height. 2 pi r times the height will give us the area of a cylinder. So that's what this is, 2 pi r times the height. And then if we multiply by delta x, our cross-sectional cylinder becomes a cross-sectional slice. The cross-section becomes a slice. So we get a cylindrical slice. So there's thickness to it, there's volume. We add it all up, it gives us an approximation to the volume, and then we do what we learned in Calc 1, take the limit of a Riemann sum, and you get a definite integral. So our integral is going to look like that. So we get more and more cylinders. The more and more cylinders that we get, the closer it gets to the volume. When we take the limit, we get the exact volume. And so then here we have 2 pi r times the height. The function f of x is going to measure the height of our cylinder. And if there happens to be 2 curves forming the height of the cylinder, we have to do upper minus lower. So this is the most general situation of that. So let's try one. The trickiest part that you will find with these shells is that you have a horizontal piece and a vertical piece always. And we have to have the radius of the cylinder and the height of the cylinder. So we're always going to have both directions, whereas with the discs and the washers, everything was horizontal or everything was vertical.
What's with the lone X in the?
Yeah, I'll show you that. That's the radius.
Oh, okay.
I'll show you that right now. So, great question. So here is our random element at x. We're told that we want to rotate around the y-axis. And if we're rotating around the y-axis, you could try to use horizontal elements and create washers. It's going to be a pain in the neck, though, because there's not a uniform right-hand curve. Right? The boundary on the right would be broken by 2 pieces. That's going to be more complicated. So when we rotate a vertical element around the axis, we're going to create, around a parallel axis, we're going to create a cylinder. So there it is. That x creates a vertical element. There it is inside the solid object. Now we know that our shape, the area of a cylinder or a shell, however you want to label that, is 2 pi r times h. That's the area of a cylinder. 2 pi r, circumference of the base, multiplied by the height, that's going to give us our area. Now, when we look over here, the radius is this distance right there. Right? That's the radius, little r. And the height is, from there to there. That's the height. Okay? So here's where that little x pops up. Isn't that what x is measuring? X is measuring the distance from the axis of rotation over to this vertical representative element. That distance right there is x. Oh, but it's also the radius of the corresponding cylinder. Right? When this little vertical element rotates around, it creates a cylinder with that radius. So that x represents the radius of a general cylinder. So this is 2 pi x. Let's think about some of our mental cues. We see a vertical element at x. We know that we're going to integrate with respect to...
At x.
If we have a vertical element at x, we have to integrate with respect to x, because that vertical element is sliding across an x interval. So we're going to need a dx. The thickness of that vertical element is dx. So that means the r and the h have to be replaced with x's, because we're going to integrate with respect to x, so we need to have them replaced with x's. So that worked out super easy with the r, because it is just x. So we didn't have to do a lot of wheeling and dealing. How about the h as a function of x? What will the h get replaced with?
F of x.
So it's going to get replaced with the function 1 over 1 plus x squared. Right? That red distance is the function. So that will be 1 over 1 plus x squared. That is going to be the area of the cylinder at x. And our limits of integration will be 0 to 2. Those are given. So the volume will be the integral. I'm going to be a little sneaky here. I'll show you why in 1 second. I'm only going to factor out the pi, not the 2. Because this is another integral where substitution is the order of the day. What do you think you would use for your substitution here if you were using substitution?
X squared.
A little more than just x squared.
1 plus.
1 plus x squared.
Yeah.
So we usually want to let u be what's in the exponent, what's in the square root, or in this case, what's in the denominator, the full denominator. So that would be our u. So let's do this. So if we let u equal 1 plus x squared, what is the derivative of 1 plus x squared?
2x.
Yeah, 2x. Isn't that now the numerator exactly? 2x dx, that's the numerator. So this easily turns into the integral of du over u. And we have a choice here. We have a crossroads. We can change the limits to u limits, or we could use temporary limits and then go back to x. It's simple enough to convert with our u equals 1 plus x squared. What would the u limit down below be?
1.
What would the u limit up top be? Perfect. And we know that this integrates to the natural log of the absolute value of your dummy variable. This will go from 1 to 5. So we're going to have pi multiplied by ln of 5 minus ln of 1. And we know ln of 1 is 0. So this will be our volume. That makes sense? So that's going to be pretty nice. Pretty nice. Say that once again?
How'd you get 1 and 5?
So the substitution, so the variables are found by looking at this ux relationship. So this says when x is 0, plug it in there, 0 plus 1 gives a u value of 1. When we plug in 2 right there for x, we get 4 plus 1, which is 5. So whatever we use as our substitution statement, that's our exchange between x's and u's. And that's how we'll change them. Okay. So these cylinders, why do we want a new technique? Why a new shape? Because a lot of times a cylinder will work better or just be a more expedient way to do it. When we look here, we're rotating around the x-axis, and we are touching the axis of rotation, which means we could use disks. But if we were to use disks, we would have to we'd have to subdivide this region into two places and do two different integrals. Whereas if we use a horizontal element here, that horizontal element at y, that horizontal element is going to be a little cleaner because we only need to use one integral instead of breaking it apart into two integrals. And that horizontal element rotated around the x-axis, there we go, there's going to be a cylinder. So when this rotates around, it creates a cylinder. Let's look at our general formula for the area of a cylinder. That's 2 pi r, circumference of the base, multiplied by the height. And now let's label things. So the radius, this horizontal element will create a cylinder with that radius. The distance that element is from the axis of rotation creates the radius of the cylinder. The height of the cylinder is going to be this horizontal distance right there. That horizontal distance will be the right x minus the left x. Anytime we do horizontal, it's right x minus left x. So, mental cue, are we integrating with respect to x or y?
X.
We have a horizontal element. How thick is a horizontal element? dx or dy? dy. So that means we're going to integrate with respect to y. So horizontal element is sliding vertically to get the whole region. So that's going to be y limits. Whereas a vertical element is sliding horizontally, so that's on an x interval, integrate with respect to x. So we know we're going to integrate with respect to y, because this is going to be sliding in this direction. So that means the r and the h need to be turned into which letter? Y's, right? We need y's. We need to write the r and the h in terms of y's so that we can then integrate with respect to y. So let's see if we can do it. So 2 pi, the radius is this distance right here. What is that distance right there? Y. Right? That's what y means. When we draw a random element at height of y, that means we're y units from the x-axis. Right? We're y units from the x-axis. The radius is the distance down to the x-axis, which is y. So y is the radius. So that's going to plop in right there. Now the height. The height is a horizontal distance, so we have to take the right x and subtract off the left x. But these are not written as x values. This right-hand curve is not written as an x value. We have to solve for x. So we add x and subtract y. Now it's written as a horizontal measurer. Now it's measuring horizontal when you isolate x. Similarly, this curve on the left right here, that's written as a y value, so it's measuring heights. We want to flip the coin, solve for x. X will be y squared. Now it's measuring horizontally. So now to get h, we've got these curves on the right, curve on the left, and we take the difference. So it's the right x coordinate, which is 2 minus y, the right x value, minus the left x value. The left x value is y squared. So right x minus left x. So we will end up with 2 pi multiplied by 2y minus y squared minus y cubed. That is our area function. Volume is integral of area. So we're going to simply integrate this. And these y limits of integration, these horizontal elements are going from 0 to 1. So that's our setup. The integration part here is fairly routine because we have polynomials. So we get y squared over 2, the 2's cancel, we get y cubed over 3, y to the 4th over 4, dy. Oh, I already integrated. Not a dy, an evaluation symbol, 0 to 1. 0 contributes no volume, so we will end up with 2 pi times 1 minus 1/3 minus 1/4. Common denominator of 12. Multiply that one by 12, multiply that one by 4, multiply that one by 3. So what's 12 minus 7? 5 pi divided by 6. So there is our final answer. All right, let's set up another one of these. These just take a little bit of, you just have to see a few of them before you can sort of start wrapping your head around it. So our shape, our region, rotating around the x-axis. If we are going to have cross sections that are cylinders, we would choose what type of element, vertical or horizontal, to create a cylinder. If we're rotating around the x-axis. Horizontal. So there is our random element at a random y. Parallel creates a cylinder. If we chose a vertical element, we would be creating washers. A vertical element with a gap would create a washer. Okay.
So in this instance, would it matter if you did like cylinders or washers?
So if we did vertical, can we solve that equation for y?
No.
No. That is a problem here. Right? Solving that hideous looking thing for y would be impossible. So technically we could set it up that way, but we're not going to be able to isolate y there to figure out the corresponding, radii. The radius, so this element down to here, that is the radius. That creates the radius of the cylinder. And what is that radius? Y. That's what right? When I draw this random element here, I'm drawing it so that it's y units from the axis of rotation, which is exactly what the radius is. The radius is the distance to the axis of rotation. So we already see that. And then the height of this is going to be that horizontal distance from here to here. So that's going to be the right x value, horizontal distance, right x value, minus the left x value. Can you tell me what the left x value is?
X equals 1.
X equals 1 over root 3. It's whatever that constant is down there. Right, that's the vertical line at that 1 over root 3.
I didn't see the root 3.
Yeah, I could tell, yeah. So the area of a cylinder, 2 pi times the radius times the height. Mental check, we see a y there. We have a horizontal rectangle. The thickness of that is dy. That means we're integrating with respect to y. That means the r and the h need to turn into y's. Well, the r turns into a y instantly. And then the height is the right x value. That is the right x value. Minus the left x value, which is 1 divided by root 3. So there is the area. Volume, 2 pi to the front. We're going to integrate. These y values are going from 1 up to root 3. These horizontal elements, 1 to root 3. So the limits of integration are 1 and root 3. We're going to cancel the y here in the denominator, so we're going to get 4 over 1 plus y squared there. And over here we'll have, let's write it as 1 divided by root 3 times y. So this brings up an antiderivative that we are going to see an infinite number of times this semester. Maybe a little less than infinite. The integral of 1, let's just do a generic one over here. If we had dx over 1 plus x squared in the denominator there. Does anyone remember from Calc 1 what that integrates to?
Isn't it tangent?
Close.
Secant?
Inverse.
Further away?
Arctangent.
Arctangent, yes. That is going to be arctangent. That is arctangent of x plus c. So, and we'll talk about why that is. You should have been shown, you should have been given it in your table of integrals in Calc 1. We'll show you why that is the case in this class. At this moment, it's just a memorization thing at this moment. But this one you are going to use a ton. And so what we see right here is that, oh, that's what we have. Right? This is just 4 multiplied by that. So that's going to be 4 times the inverse tangent of y. Minus, here we do the y squared over 2 thing. And the 2 gets multiplied by the root 3. And we're going to go from 1 to root 3. So we have that. Unfortunately, both limits of integration contribute to volume here. And we have to remember a little bit of our trig again. So, 4 arctangent of root 3. When you're thinking of your unit circle, the terminal ray, so that's the ray that goes right through the origin, tangent and slope are the same. So if you're at 45 degrees, what's tangent of 45 degrees? 1. That's the slope of the terminal ray through 45 degrees. When we go up to root 3, so arctangent of root 3, that's going to be the angle that has a slope of root 3. When we're on the unit circle down here at pi over 6, that has a slope of 1 over root 3. When we're up at pi over 3, that's going to have a slope of root 3. So arctan of root 3 is the angle with a slope of root 3, which is pi thirds. So that's going to be 4 times pi over 3. Minus, plug this in here, we get 3 over 2 root 3. We'll simplify that in a minute. Now we subtract off what we get at 1. Arctan of 1, angle with a slope of 1. We just said it. It's pi over 4. So that's going to be 4 times pi over 4. And then minus a minus, we get 1 over 2 root 3. So that's what we get. Let's stop there. I'll simplify that and just continue on for a minute and simplify that. And you can go on your merry way. You can stick around. I'll stay around as long as you want and answer questions. The first question I have is, did it record the screen this time? We'll find out in a minute. It better have. So yeah, if you have questions, just stick around and I will go over them with you. And I will just simplify this so you have the simplified answer once you look at the notes. So root 3 minus 3 root 3 is minus 2, so one more step. I guess those have a common denominator.